Okay, hello everyone. Welcome to the first quantum conversation session of the year. In this session, we're going to be hosting QC Ware. So Matt Johnson, the CEO from QC Ware, will be joining us. And in addition to that, we'll have Wim van Dam from the US head of algorithms. QC Ware has a special place in my career and education, because I did an internship there. It was actually the first internship I did related to quantum computing. It was the first time I saw that I can do what I really like to do and I can get paid for it. So thank you, QC Ware, for that. And Wim was actually one of my supervisors for the project, and he wrote my letter of recommendation to the PhD program at Oxford, which is where I am now. So yeah, again, like QC Ware was a springboard in my career and education. And yeah, so as in our tradition, let's go around and let's ask people to introduce themselves. We have a larger crowd today, so let's just do like name and where are you joining from. You can say like I'm like the university or like the city or any like a company name. Just very quickly, let's just have a chance to like introduce ourselves, and let's start with Matt, if that's fine, the speaker, and then Wim will be joining us at 11 a.m. PT, maybe a bit earlier, that's what he said. And Wim will be talking about quantum optimization, while Matt will in general talk about the quantum computing landscape and QC Ware. And if that's possible, Matt, maybe you can also mention some career opportunities at QC Ware as well for the students here.
Great, Mert. Yes, first of all, thank you very, very much for having us. I really appreciate this, Mert. And thanks for being dogged about it. I'm looking forward to it. Yeah, Matt Johnson, I'm the CEO of QC Ware. I'm in Palo Alto. And over to the next person.
Okay, I'll just call out names. Alexei is actually the creator of Quantum Conversations. Alexei, are you around? Hey, Alexei.
Yes, hi guys. Thank you very much, Mert, for taking charge on this. It's great to join. I'm moving around the area, juggling many things, so unable to stay for a bit, but super exciting to have QC Ware presenting. So I'm currently community director for XIII Discovery at IBM, where we bring together basically data science best practices to all of science. Right? So this is a very ambitious plan. We just started out. And so quantum is one of the tools in the palette alongside AI and a hybrid cloud. And so we basically aim to disrupt the whole scientific method by, doing what data science did for AI to all verticals, right? Material science, biology, chemistry, and quantum is instrumental in a lot of it where, you cannot handle normal kind of classical workloads, right? Modeling proteins, discovering new materials, obviously huge potential. So I think super excited, that we have these conversations around the world, and happy to meet everyone.
Great, thanks, Alexei. We also have Noah here, also from the Stanford Quantum Computing Association, one of our partners.
Hey, I'm Noah. I'm a graduate student here at Stanford. I work on theoretical quantum computing, quantum information theory, with an interest in algorithms and algorithm science. So this talk is going to be particularly interesting to me. Through the Quantum Computing Association in the past, I've done a lot of outreach work, both here in the Stanford community, organizing journal clubs, and outside of the Stanford community, organizing teaching at the high school level about quantum computing. So if you have any questions about things like that, feel free to ask me.
Thanks, Noah. Okay, so we have a lot of people actually here now, so I don't want to take more of our time. So what I'm going to do is I'm going to call out everyone, but if you don't want to speak, usually I wait 10 seconds for actually everyone to have a chance to introduce themselves, but I'm going to wait just 2 seconds instead. And if you don't want to speak, you can just you don't have to say anything. So Nathan, do you want to chime in here?
Yes, quickly. Hi, I'm Nathan Shore. I'm in the Silicon Valley, and I have this site called quantumcurious.org. It's material curated solely for beginners. You know, you get into quantum, how do you learn it? You get this floodgate of information. A lot of it is too technical at the beginning. So what I did was filtered stuff that I used in my own learning, put it on a site. I also help hold up community meetup events in a local area. And that's it. Now over to the next person.
All right, great. I see someone raising their hands. Actually, that's a great way to do it. Melis? Okay. Mark? You want to introduce yourself?
Hi, I work at Quantum Computing Inc., developing quantum applications. Looking forward to your talk.
Thank you. Jion Zhang?
Hi, this is Jiong Zhang, and I'm from Stanford Research Computing Center, and I'm working on algorithm applications of quantum computing for computational chemistry problems and machine learning problems. Thank you.
Thank you. Anjis Huang?
Hello, I'm an undergrad student at UC Berkeley, and I'm part of the UC Berkeley Quantum Computing Club. I'm working on computational high energy physics, and I'm interested in quantum computing.
Great, thanks. Asmul? Okay, Augusto.
Oh, hi. I'm a quant dev located on Buenos Aires, Argentina. I try to join every time I can. So nice to see you, Mark.
Nice to see you again, Augusto. Augusto, I think, was one of our speakers before I joined Quantum Conversations. Am I right?
No, I didn't speak. A partner of mine back then on JP
Like
Morgan.
a general member of our sessions. Yeah, really nice to see you again.
Yeah.
Cici. So Cici, also, I worked with Cici when I was at Fidelity Investments. Really nice to hear your voice again, Cici. You want to say maybe like a few words about yourself?
Sure. I'm program manager supporting the emerging technology team at the Fidelity Center for Applied Technology, where we're looking at quantum. And I did forward your invite on to some of the other colleagues and hoping that they might be able to join. And I see Seema was able to join. Seema's joined our team recently.
Great, great. Thanks. That's great. Jan is a student at my program at Oxford.
Hey guys, so I'm a few doors down from Mert, and I work on quantum optics with single photons from atoms. Yeah, and I'm glad to join in.
Great, great. Thanks for joining in. And Juan also just joined. He's also in Jan's group.
Yes, hi. Nice to meet you guys. Great to join this initiative, and yeah, thank you very much for letting me join.
Thanks, great. And Fazlı Berk Ördek.
Hi, it's a pleasure to meet you all. First of all, this is Fazlı Berk. I'm just graduated from the Erciyes University Electrical and Electronics Engineering. Currently doing my internship at Google Turkey as a software engineer, junior software engineer. I just wanted to continue my career as a quantum developer, but looking for some master or PhD opportunities. It's good to be here. I'm just know something fundamentally, but I'm looking for more and more. It's a pleasure to all meet you. I hope we get better and better this concept, and I'm really huge interest with your own experiences. I'm curious what's going on right now. So, hi again.
Thank you. Jamie's also one of our regulars. He was also at the conference hosted by QC Ware, Q2B. Hi, Jamie. Okay. Okay. Quran.
Hi everyone. I'm from India, and I've been attending QC conversations for the past quite a few sessions. It's quite nice to learn. Thanks to Mert and Alexei. Thanks.
Thank you. Nice to see you again. Michael or Michal. Michael. Sorry if I'm butchering the name.
Hello, so you can call me Mike. I'm visiting Stanford right now. I'm doing my PhD in quantum information theory. I'm looking for opportunities around Silicon Valley to work as an internship, and I'm joining through the link provided by Stanford Computing Association.
Great, thanks. Peter.
Hello. Yeah, I have a company called Feynman Solutions, co-founder, and we are working on quantum simulation algorithms based in London. Hello.
All right. Seema.
Hi, I'm from FCAT Fidelity, as Sisi mentioned, and I'm joining from Colorado today.
Thank you. Tom. Tom is also a student here at Oxford. Sorry.
Yeah, hello. Yeah, yeah, I'm at Oxford doing a PhD in physics, and I'm kind of focusing on methods for error mitigation for near-term quantum computers.
Uchenna?
Yeah, I'm a developer quantum computing Inc. in North America, and just here to learn.
Thank you. Zai?
Hey, I'm Zhao Yi. I'm an undergrad at Stanford University. I'm currently working on something related to quantum computation, cluster states, error correction stuff. I'm just interested in quantum computation in general. Nice to meet you.
Thank you. Nice to meet you too. Zibo.
Hi everyone. I'm a graduate student at UC Berkeley, and I'm working on quantum error mitigation, variational algorithms, and quantum machine learning.
All right, thanks. If I missed anyone, feel free to unmute yourselves and introduce yourselves. Otherwise, we're going to move on.
Yeah, my name is Siddharth. I'm a student at UC Berkeley. I've been for a couple of these meetings, and I like coming to them. So here I am again. Thanks.
And hi, I'm Melis. I'm intern in Stuttgart University. I'm working with Prof. Raptrap right now. Yeah, that's all my side. Thank you.
Okay, so we can go ahead and get started. Just before that, I want to mention something. So the reason why we do this, I think I first saw this when I first joined Quantum Conversations with Alexi, because the thing we're trying to maintain here is like a discussion format. So if that's fine with you, Matt, let's keep it as a discussion. And while you're listening to Matt, if anything comes up, feel free to unmute yourselves and ask a question, and also we'll have some time in the end for questions as well. Yeah, and again, Wim will be joining us after Matt.
Yeah, okay, let's go ahead and kick off. First off, as a preamble, I really like the vibe of these sorts of community kind of gatherings. So I appreciate the way Mert kind of had everyone introduce themselves. You know, for I think a number of people on this call, quantum computing has been around for a long time, maybe since Feynman's paper in '82, or maybe, you know, you could say there's some legacy long before that, but actually, you know, the actual industry is just starting to form, and certainly we don't have any industrial or production ready quantum products out there yet. As a matter of fact, you know, certainly not in quantum computing, and it could be that somewhere out there in a production workflow, in, you know, some recesses of some, I don't know, some nation state, maybe there's, you know, a quantum sensing, timing, or metrology thing that's working, but that's kind of it. And so, you know, I think that everyone on this call, particularly those that are students, and there are a lot of them, I think you've got a very, very fortunate opportunity ahead of you. First of all, you've got, you know, a lot of brain power. I think anyone in this call that's tackling quantum mechanics curriculum and quantum computing, understanding the formalisms is, quite lucky to be gifted intellectually, cognitively like that. And I do really think that if we look forward probably 20 years, 25 years, I think quantum technologies are going to be embedded in just a large range of the things, the systems that we touch every day. And it's probably hard to visualize that right now because we really don't have clarity on some of the first, big killer applications of quantum technologies and quantum computing, but that will come. It does feel like it will be one of these, kind of exponential growth things, kind of like, if you look at the ARPANET, which, transformed into the internet, and, you look at the number of nodes that were around in the late 60s and how that grew through the mid 70s, and then the 80s, it sort of had this, very slow burn, but certainly an exponential curve. And I do think quantum's like that. So I would just say, from my standpoint, I feel all of you on this call are, really well positioned to have some really fun things to do. And just on that note, I recall when I started getting interested in quantum computing roughly 8 years ago, I had zero background in computational technology. And I had moved out to Silicon Valley, to Palo Alto, and there was nothing happening out here then. Rigetti in 2013 raised a seed round, and I met Chad Rigetti in 2014 actually out here. So I was in Palo Alto, he was up in Berkeley. And that was sort of my first contact with anyone that had formed a quantum computing company. So nothing was happening in the Valley then. And fast forward to today, and it's starting to bristle with quantum computing. As a matter of fact, I think at the application layer in quantum computing, just the application layer, there are over 50 startups. That doesn't even count the big companies doing quantum computing. Over 50 startups that have seed funding or beyond. So they're capitalized. They have at least a small team, and they're moving forward. And there's almost as many, almost 50, doing infrastructure software, so quantum programming and processing tools and methods. So there's a ton of that out there, and keeping in mind, this is before hardware and software is even performant. And it's also the case, I recall, if you go to in the United States, if you were going to an undergraduate, let's say a physics or computer science course or department, almost none of the students back then, undergraduates for sure, knew anything about quantum computing or had even heard of it. And that's completely changed. If you go on to any research university that has, an undergraduate component, everyone in CS and physics and EE has heard of quantum computing, and is their interest level and awareness level is really increasing. So this has happened like almost overnight. But all of you you do have really a head start. I really can't see for your own careers in academia or industry, I think the future is going to be very bright for you. Whatever you end up doing, I just think you're very fortunate for this. You don't necessarily see that because you're just hopefully having a good time as students, and you're not trying to necessarily conquer the world or look at the big picture of all this, but this technology is really going to change. It's going to be very, very impactful. So anyway, yeah, go ahead, Mert.
I definitely agree with that. Like when I joined Stanford in 2015, I was intellectually interested in the subject, but maybe 2015 is a bit late. There was some stuff started happening, but I saw that change throughout my undergrad career, and there was just one class, and every term I would just look at the course list and try to find something related to quantum computing, and maybe there were a few classes offered at the time. And now Adam Bullen, who worked at QC Ware, is Stanford's first faculty that's gonna do fully quantum computing.
Yeah, and because when you think about any innovation that happens in industry, it almost always invariably has its roots in academic research. And so Adam Boland, I met Adam 5 years ago I had heard about him, and I was down in Palo Alto, so I drove up to Berkeley a couple times where he was doing a postdoc under Umesh Vazirani. And I asked him to come on board with us. And so he was part-time with us for 4 years. And now at Stanford, he's an assistant professor. So he's down to 1 day a week, and that's fine. We work well with him. And the other person that's in a similar situation, we had a postdoc, a guy named Peter McMahon, who had completed his PhD at Stanford and then was a postdoc there for 4 years. And during his time, he had a 50% appointment with us. Now he's at Cornell as an assistant professor. He's 1 day a week. But, you know, and that kind of brings us to fast forward just a little bit to move the conversation. So just a little bit of structure for this next hour and a half, I guess. Wim van Dam will, in fact, be joining. He'll be popping on. Maybe he already did. He's probably going to come on before 11 a.m. And if we start to kind of taper off on sort of the business and industry conversation, he's going to pick right up and get heavy duty technical with you. So I'll be talking more at the business level. And, you know, Mert did ask me, by the way, to talk about career stuff, and I will. So to sort of kickstart that, I included on the chat box the email address for a guy named Sean Weinberg, who's one of our quantum engineers, and he's also just helpful generally. And what we're really looking for are people who can design and develop quantum algorithms. And we do a lot of things in our company. That is, for us, the most prized skill set. And I'll talk about why that's the case in just a minute. So if you're finishing a PhD on the theory side, we definitely would like to talk to you. If you're not quite there yet, certainly get in touch and we can you know, establish a connection. But we're hiring very, very aggressively in that area. What I can do right now, I'll talk just a little bit about QC Ware, and it's not meant to have me pound my chest or anything like that. I just want to give you the background on the technical program that we have and the business that we're developing. So just to start out, QC Ware is a quantum computing software company. We set up in 2014 in Palo Alto. And the thing that enabled us to start out and get access to quantum computing hardware, which was quite scarce back then, was we had a collaborative research agreement with NASA. So NASA in the United States has, I think, a total of 15 research centers and space centers all over the country. And one of those research centers is called Ames Research Center. It was named after an early director of the predecessor to NASA, a guy named Robert Ames. But in any event, Ames Research Center is kind of like an incubator for new technologies. Back in the 1970s, for instance, out at Ames, they had a big thrust on vertical and short takeoff aircraft. They also have been involved in the design of manned space flight, so life support systems and spacecraft. They do small satellites. They do all kind of earth sciences. They do all sorts of things. They're like an incubator. And back at the end of 2012 or 13, Ames Research Center said, okay, we do some theoretical physics work. Let's get into quantum computing. So they set up a quantum computing group, and it was run by a guy named Vadim Smilyansky. He was the real brains and energy really behind this, and he pulled together people that didn't necessarily have a lot of background in quantum computing, but a diverse physics background. He pulled them all together and set up this thing, and it was really, I had a lot of respect for how he did that. In any event, I got to meet him at the end of at the end of 12, beginning of 13. It took us 18 months to sign an agreement together. So QC Ware was set up on the basis of that. And through that agreement, we got access to a machine at NASA Ames, a D-Wave machine that Google had purchased and had installed at Ames Research Center. Google's in Mountain View, Ames is in Mountain View. So it kind of worked out. It was a public-private partnership. And that allowed us to start programming on that form of quantum computer. Now, of course, there were no gate model machines that were exposed at that time. And in the meantime, probably 90% of our research, 95% is in gate model systems. So in any event, there's Wim van Dam, by the way. He just popped up. Wim, we were talking about you just a little bit.
Yeah, we already introduced you, but do you want to say hello, or do you want
to? It's great to be back in Oxford. Can I say that?
Yeah. Yeah, this is a new building now. I'm at the Beecroft building.
Okay. Okay. So, but Wim will give a deeper background. I mean, one of his 2 PhDs is from Oxford. So in any event, what we decided to do at QC Ware was to focus on trying to be the first company, the first software company that could deliver performance to enterprise customers. Remember, we're a software company, we're an enterprise software company. So the trick is to provide something useful software-wise to companies. And so when we thought of that, okay, so we've got, you know, very nascent quantum computing hardware. We have on the gate model side, we have, you know, noisy quantum processor, NISQ quantum processors. And on the annealing side, of course, we have the D-Wave machine and others that will be coming out, but very kind of early generation and not capable of instantiating a production size problem or running anything with a speed advantage. And so we decided early on that the most important thing for us to be able to do would be to design quantum algorithms that run on NISQ hardware, thinking to ourselves, look, when error-corrected machines get there, or when they become close to getting there, then we'll pivot back to focusing on error-corrected algorithms. But we think that, you know, part of our thesis as a company is that it's going to be some time. I don't know if that sometime is 4 years or 12 years, but let's say it's around, so somewhere in there. And maybe 5 to 12 or 7 to 12, I'm not sure, but we don't think that error-corrected machines are going to be available for some time. And so instead of just, you know, orbiting around and doing basic research during that time, we thought we'd step up to a much more difficult challenge, which is designing algorithms that are resistant to noise and that can do useful work for companies. So really our starting point, and by the way, just so that's part of our company philosophy, that, okay, we're going to make things work on NISQ hardware. The other part is that we believe it's essential that we are very close to customers so that we develop an understanding of what their hard problems really are and what the mathematical structure of their problems are. And so I do think, and this is not meant to pound our chest necessarily, but our company, I think, is definitely the leader in securing revenue generating projects from big companies. So our customers that we've announced include Goldman Sachs, Airbus, BMW, Total, British Petroleum. Who else can we, Wim can help me out. XIII, which is the largest bank in Latin America. We have undisclosed projects with one of the 3 biggest automotive OEMs for battery chemistry. To make a long story short, we've signed almost 50, closing in somewhere between 45 and 50 customer contracts since inception. And the bookings, the revenue that we have booked, or the orders that we have booked, is somewhere between $13 and $15 million. So this is really, this is quite, I think it's dramatically ahead where most of the startup community is in terms of revenue generation. And we're very proud of this. And it's really the other part of our thesis, because when someone's writing a check to you to develop a prototype application or a bunch of, you know, code base that's runnable on quantum machines, they're doing it, if they're writing a check to pay you, it means that they're genuinely interested. You know, anyone will do a non-paid collaboration. As a matter of fact, you know, that's the easy part. So how is it that QC Ware has been able to secure all of this business, all of these research collaborations? It's because we have managed to pull together an extremely strong team of quantum algorithms experts, and Wim runs one of those teams. The other teams are in quantum machine learning, that's run by Jordanis Karanidis, and in chemistry simulation, and that's run by Rob Parrish. So we are fanned out across those three problem classes, because that's where the part of our thesis is that in each of those domains, there will be speed ups that will be achieved for industry problems. So really, people are what they're paying for right now is the expertise of our team, which is why I mentioned early on, we are hiring, and we're hiring very aggressively. And we want to build the largest and strongest team of quantum algorithms experts for NISQ hardware in the world. So if you really cut it that way, that is our objective. And we truly do want as a mission to be the first company where enterprises say, if I want speed up on quantum hardware, I'm going to go through QC Ware stack. And so that's what it's all about. Let me stop right there and see if there's any questions about this or anything else, because I just don't want to ramble. Anything? Okay. Let me talk just really briefly about our product then. Perhaps a visual aid will be helpful. Okay, we can't share. So basically, the core of our company, although most of this revenue we've generated is from services, people paying us to develop algorithms. The product that we've built, I think, is pretty ingenious, and I think it'll be quite effective. It's a service, actually a set of services that run and are currently integrated into Amazon Bracket, and will be integrated into Microsoft's Azure Quantum, and will be integrated directly into other hardware backends. And I'd prefer not to announce those publicly because we're doing these things offline, but when they become public, you will hear about it. But effectively, we, another part of our thesis, therefore, and this is part of our product thesis, our customers don't know which hardware backend will win the race. And right now there are something like 45 commercial quantum computing companies that are building full-scale quantum computers. And they're all run by, I think, very gifted and responsible people. But it's really unclear to the user community which group is going to field the first performant quantum computer. And it's unclear whether even that group will be able to sustain a monopolized position in hardware. And so we feel, to support our customers, we need to remain independent, and we need to have our algorithms runnable on all the backends out there. And so therefore it's important to us that we have a product that can target, that allows our users to target all those backends. So of course, through Amazon Bracket, Amazon is spending a ton of time trying to integrate more and more backends into its service. Azure Quantum is doing the same thing. You have IBM, which is receptive to having services like ours run on its hardware, and we've done a lot of work with them and with the other hardware vendors. So we're really part of the thesis is, let's just make sure we have access to all the hardware backends out there, so that when one of those vendors is the first to achieve really quantum advances in the hardware layer, like, our customers can exploit that. And on that note, another thing that's happened in our company is up until last year, I think everyone in our company, with maybe one or two exceptions, I'm one of those exceptions, it was a quantum algorithms researcher, a quantum engineer. And it's just now that we're adding a little bit of a thin but very efficient business wrap around that. So to build this product, or to build out this product I've mentioned, we've hired someone named Christoph Siegert from Microsoft, who did his PhD in quantum computing at Cambridge. He's an experimentalist. And then he was working at Microsoft for 7 years, did an MBA, and then was working at Microsoft for 7 years as a senior product manager. So it's kind of like, that's sort of an ideal background for us on the business side. So we're very selectively continuing to hire more business people as well. But for those of you thinking about a career opportunity, I think something that's quite interesting about QC Ware is I guess another part of our thesis then, so we don't hype. We have really strong ambitions, but we're absolutely the last company that is going to pound its chest and just puff things up. I realize that founders of companies need to keep their companies funded. And one way to attract venture capital funding is to overstate what you're capable of doing. This is kind of natural. And actually, you know, if you're the CEO of a company or a founder, it's your obligation to keep the company funded. And so you'll push the limits. And I do think pushing the limits and being extremely optimistic is fine, but the line gets drawn when it becomes misleading. And that's something that we never, ever want to do. And so what we want to do is like lead with substance. So when we say, what is the goal of our company? It's to be the first to achieve a practical speed up for an enterprise problem. It'll probably be in chemistry simulation, but that for us is just really imperative, that our reputation is one of substance. And one thing I think that indicates we're winning in that, it's not just this wide range of commercial customers, but we've been successful at winning a number of government research grants from the National Science Foundation, the Air Force Office of Scientific Research, the Air Force Research Lab, the Department of Energy. So these are work streams that, you know, require true rigor. And so like this is really important. And we're going to continue to do all that. Let me just stop for a minute there again and just ask if there's any questions about our company or about what we're doing.
Matt, hi, Peter Morgan. So yeah, you say you have 30 to 50 million revenues from company in clients, end users. I mean, that's great for you guys, QC Ware, but are they seeing any revenue from that? Or is it mostly R&D for these guys?
It's 100% R&D. Yeah, there's nothing that you can do with quantum computing resources, algorithms or software that will give you any speed up. And so here's what these guys think. You take a big, huge company like Goldman Sachs. So, you know, they spend their IT spend annually is like $1 billion, $1.5 billion. And probably double that in terms of, 25% of their staff are technology people. So what they're thinking is, okay, here's these emerging technologies that we will someday build into our workflows. Someday we think we will, but we don't know when or in what form. So for them to spec $250,000 or $500,000 a year or $1 million a year to get smart in this is absolutely nothing to them. You know, this is a trivial amount of money. So when we book all of this revenue, as I said, you know, 13 to 15 million, it's somewhere in there that we booked. This is made up of, you know, 45 to 50 different customer contracts. So there's no one company that says, wow, we see a direct return on investment right now, so we're going to triple down on this. All of them are just speccing or seeding small amounts of money right now. Now this is changing, and we're seeing on the pharma and material side, those companies see a little more direct line to performance, perhaps in the next 3 to 5 years. And for them, it's becoming not like a 10-year speculative thing, but a more deliberate, algorithm and product development program for them.
Right. So, yeah, I mean, we're basically waiting on the hardware, right, Matt?
UK thing or something about quantum conversations tomorrow, Wednesday.
Sorry, I don't know. Greg or Peter was saying something. I think we got talked over there. But and then Noah has his hand up. Yeah, go ahead, Peter.
Yeah, I was just finishing off there, Matt, with a kind of observation. We're just waiting on the hardware, right? I mean, there's not going to be much revenue before the hardware. Or?
Well, yeah, I think most people would say, well, you can also get efficiency gains out of better algorithms. And I'm a layman, Peter. You're probably a heavy-duty technical person, but as it's been explained to me, you know, the way I look at quantum algorithm development, the trick with NISQ hardware, yeah, it's going to keep progressing, and qubit quality and gate fidelities are going to continue to increase. But the trick is really to design for an algorithm to to minimize the number of gate operations or steps that have to be performed on the hardware as the problem gets executed on hardware. So really, you're trying to have the most efficient mathematical solution to the problem, minimizing the number of steps.
Right.
And so there is room to pull that deployment forward of quantum computing. There is definitely room on the algorithm layer to make an impact, and that's what we're doing. Okay, we're part of that overall effort to try to do that.
Sure. Okay. Thanks, Matt.
Gregory, did you have a question, or was it just?
No, I didn't have a question. Thank you.
Okay.
Noah, how about you?
Yeah, no, I think you have a question.
I have two questions, and the first is more about the business side of things. I'm just interested in MBA things in general. And I was curious to ask you, Matt, do you still consider yourself a startup? Like, in what stage of funding are you? You mentioned all these revenue streams. Is QC Ware in the green, or can't you tell me that? Would you have to kill
Yeah,
me?
no, I can, Noah. I really appreciate that kind of question, though. I know you introduced yourself as, what are you? Are you at Berkeley, Noah? Where are you?
Ouch, I'm so hurt. You've forgotten already. No, I'm here at Stanford. I'm part of the Quantum Computing Association here. Yeah.
Okay, sorry. Well, come by our office.
No worries.
But come by our office sometime, Noah. Seriously, we're just email me afterwards and come by. The question that you asked is actually the one I get most fired up about. Okay, it's a brilliant question. I think what I've always wanted to do in quantum computing was I've always looked at this as saying, look, I want us to build a business. I don't just want us to develop a feature or a capability or something. I want a real business. And that's why I thought it was really important. We're still in the foundation business building thing, but we have a sales and business development group, a very large research group, a product group, an operations group, an engineering group. We have everything that a big software company has, and it all works together. I think to really have a business, what you need is a team, a product, and customers. And so really everything that we're doing is pushing on all those streams at once. In terms of financial performance, no, yeah, I can tell you, we have lost somewhere between $500,000 and $1 million each year in 18, 19, 20, and 21. So for the last 4 years, our overall cash burn for the entire year has never exceeded somewhere around $1 million. And the reason for that is we cover between 80 and 90% of our operating expenses. That's paying people's salaries, paying office rent, paying lawyers for IP prosecution, all that stuff. We cover 80 or 90% of that with customer revenues. So we've intentionally kind of sized the company and grown the company staffing. We haven't gotten over our skis. I, rightly or wrongly, always considered it to be probably the wrong thing to do, to just mimic the startup template that a standard startup does, where they ramp up super quickly. And the difference is, philosophically, between a deep tech startup like ours, or a company, let's say, and a normal one is this. In a normal startup, the window's open for some kind of product innovation. It's like open, and you have all these startups trying to get through first. And the way they all think that they're going to get through first is, let's raise a bunch of money, let's develop a product, and then see if it works. Well, in quantum computing, the real production window is just starting to crack open. And so, I'm trying to calibrate how quickly is that window coming open, and the rate of opening of that window is really how quickly the hardware is developing, and to an extent, how quickly our algorithms are. So as we're like at 35 or 40 people now, I'm starting to feel more firmness in the customer market, which encourages me to ramp up more quickly. But even now, what we've always had is part of the psychology of the company. We never wanted to reduce our standards for hiring people, like in terms of the qualifications and the fit of these people. For the first 7 years of our company's life, we never lost a full-time employee. 7 years of existence, 0 attrition. We had a couple people go recently, 2 of them, very good friends. They're effectively the founders, or almost at a founder level of another company. And I worked very hard to try to keep them. I couldn't, but I love them. But I found out, okay, I can't keep everyone forever. You know, I've always treated the company like a family, where if anyone was even thinking about leaving or somewhat slightly disgruntled, I was all over it to try to figure out how can we make it work. And I don't think you can do that forever. I mean, eventually children become adolescents and then they grow up and then they leave the house. I mean, this does happen sometimes, and I understand that. You know, so your question, Noah, is really, I really like the way you're thinking about it, because yeah, I would like QC Ware to be as big, as powerful as Oracle became, you know, in the 90s and early 2000s. There's some parallels between what we're building product-wise and what Oracle did. I mean, in an abstract way, you know, a relational database management system unleashes the power of a relational database and lets customers use it in the same way that we're trying to take quantum computing hardware and make it useful. And the way we're doing it, of course, is zeroing in on specific industry use cases and tailoring a quantum algorithm that will solve the hard part of that problem very efficiently, and then combining that with classical co-processing, putting all of that into a code base, and that's a service. That's one of, you know, several. That's one of a series of services that we're going to be launching. But so yeah, I also don't think, you know, we raised 3 rounds of finance. We've raised in total around $33 million, which is a lot less than some of our peers. And I'm like, what are you spending your money on? You don't have any revenues. You don't have a visible product. What are you doing? And I don't mean to malign them, but I look at it differently. Like I want a very, very focused product development that's informed by what our customers are telling us they want. And so with like 25 in the bank, I think this year we might burn between 3 and 5 million. And it's a little too early to estimate what we'll burn in 2023, but that's not constraining our hiring. Like I want every single highly qualified, credentialed person that we can attract on the algorithm side to come into our company. So I'm not going to throttle back on that. But typically when startups raise money, they size the round to last them about 18 months. And like for us, since we're near break even, I don't think we'll ever have this existential thing that most startups do, where they kind of lurch from one round of financing to the next and kind of have a panic thing. I don't want that. And so in answer to your other question, do you consider yourself a startup or not? I consider ourselves a startup in that we have the potential to grow very, very fast. So we've grown revenues at about 50% a year, and that's pre-production. What we're going to be able to do when hardware gets more powerful is accelerate that growth. So from that point of view, we're a startup. But if you were to spend a day inside of our company, you would say it is missing that. I mean, we don't do any yelling and screaming. There's not like a lot of anxiety. There's certainly strong differences of opinions on a lot of things. But I think it's really important that people like Wim, who comes from an academic environment where there's open collaboration and there's thoughtfulness, I want us to preserve that. And because I want people like Wim to thrive in that. You know, when you think about it, General Eisenhower, you know, who was I guess his title was the Supreme Commander of Allied Forces in Europe, but eventually he became the overall chairman of the Joint Chiefs, kind of. But he had this really simple, interesting thing. He described how to efficiently run an organization, what an organization should focus on. It was a 2x2 kind of grid. On the y-axis, or a quadrant, on the y-axis, he had things categorized as being unimportant and important, and on the x-axis, it was not urgent and urgent. And so you have these four kind of quadrants. And he said, what most organizations do, they focus on things that are urgent and not important. And that's terrible. You know, you don't want to do that. What you want to do as an organization is focus on things that are not urgent, but very important. And that's what I think one secret is. If you're trying to innovate, trying to develop new systems, new algorithms for quantum computers, I think that's required. This sort of, let's just keep thinking about this. Let's collaborate. Let's take inputs, you can't really rush that kind of thing. So that's kind of the vibe of our company. So it doesn't feel like a startup, but I think it's growing, very quickly, like a startup does. Did you have another question, Noah?
I did. I have a million follow-ups from what you just said, but I won't ask them for the sake of time. I will say though, congratulations on your revenue. I feel like I've lost more change on the floor of my car, so you should be very proud. My second question was more on the technical side, and I'm just curious: is QC Ware more focused on theoretical algorithm development, or is there like some heuristic testing that you do as well? And if so, like what hardware are you using? Because you said you didn't want to commit to a certain hardware infrastructure.
Yeah.
Do you use AWS? Are you using IBM to do heuristic testing of algorithms?
I'll let Wim. This is a perfect segue for Wim to jump in here. But the bottom line is we've run on literally everyone's hardware that's out there that has something exposed, and we run through Bracket, we run on Qiskit, we run on Azure, and through Azure onto their, I don't know how much we've done through Azure onto their backend. But Wim, why don't you go, if you can, give a more technical answer to that?
I think before that, I think we had another question for you, Matt. Someone raised their hand.
Let's do that, Mert, because here's the deal. At 11 o'clock, I have to jump. And
Yes.
so let's get like but Noah, just hold that question, okay? So we have like 5 or 6 minutes if there's any more business questions that I can answer.
Great, thanks. Someone raised their hand but quickly dropped, so I couldn't catch. Can you shout out if you have a question? Yeah, so any more questions for Matt? Because after that, we're going to be focusing on quantum optimization and more technical stuff with Wim.
Okay. So one thing I would say, 1 second. Mike, you said when you introduced yourself, Mikal, Mike, just email me here. Hold on. My only closing statement is as I said, I have a ton of respect for what all of you are doing academically. We would love to talk to anyone who's focused on quantum algorithm development that would seize on the challenge of trying to have these NISQ era quantum computers do useful work to achieve, practical speed ups. This is a very, very hard thing to do, but it's what we're all about. So if you have interest in that and you think you can add to our quantum algorithms program, we would absolutely love to talk to you. So, and I thank you a lot for the time here. I'm sorry that I have to jump, but now Wim can get into the interesting technical stuff with you guys. But thanks a lot, Mert.
Yeah, thanks, Matt. It was great. Thank you so much.
Bye-bye.
Thank you, Matt.
Bye.
Okay. So yeah, Wim will be speaking. We already introduced you, Wim, so you can just jump in and.
Oh, okay. No, I don't know what you said about me. Okay, so,
I thanked you for writing me a letter of recommendation and that you did your PhD at Oxford, and I worked with you on my project at QC Ware, and your bio is also in the announcement. I think no one asked you a question though, so maybe we should start with that.
Sure. I mean, I'd rather than hearing myself talk, I love to be interrupted. To kind of go to the hardware question, there are all these platforms, but at the lowest level, we have run and tested our algorithms on the D-Wave annealers for certain optimization problems. We've run it on IBM's superconducting quantum circuits, the various ones that are available, some of them which are not publicly available. And we've run on IonQ's ion trap machines. Those have been kind of our main workhorses. We've done some stuff with Google, we've done some stuff with Rigetti, but those are kind of what we've worked on. And as I will be kind of talking about soon, getting an algorithm, designing an algorithm is just the beginning. Then you have to implement it, you have to test it. There's a whole range of things that need to go well before you have a successful commercial product. And so running simulations, doing kind of like sanity checks. Okay, my algorithm runs on paper, now let's see how it runs in real life, is extremely important. And so we also do a fair amount of quantum algorithmic design, and then we run them on simulators, some with noise, some without noise. Because yes, my background is in theoretical computer science. I did my PhD at the University of Amsterdam in CS, and a PhD in physics at Oxford. Then I went to the group of Umesh Vazirani at Berkeley, because of course in the Bay Area, Berkeley is the leader and Stanford is the follower in quantum computing. That was in the computer science department. And then at UC Santa Barbara, I was a professor in computer science for a joint appointment in physics, which is to say that I'm mostly a computer scientist and only less so a physicist. And the way you learn algorithms in your typical theory course in a university is the rigorous analysis, the big O analysis, the epsilons and deltas and so forth. And of course, this is extremely important. Once I started talking with customers working at QC Ware, there's like this whole other world that kind of you become aware of as a theoretical computer scientist, that the way people run algorithms in practice is quite different. People solve, NP complete, NP hard problems all the time because they have to. And so people settle for algorithms that run approximately, or that, are going to work well kind of on average. And so there's this whole aspect that you have to address before you really kind of deliver something that a customer wants. And so I've got some slides on my experiences as somebody who was brought up in the complexity theory kind of world in quantum computing. I've got my whole academic career has been about quantum computing, and like how this translates when you try to kind of adjust this or use this in a commercial setting. And I'm going to try to share my slides, and I think somebody needs to flip a switch if that has not already been done.
You can share now.
Oh, perfect. Thank you. Where do we go? Yes. Okay. And I'm not going to ask the dreaded question, can everybody see my slides? I'm just going to assume that if people don't see my slides, at some point somebody will pipe up. Okay. So quantum optimization, that's my specialty at QC Ware. And just to kind of like tell you about how you kind of address solving optimization problems, with quantum computers. So here are some of our, well, I should say not some. Here are like all the customers that we can disclose. Some of them are indeed US government related, and some of them are the names that Matt mentioned earlier. And so with our customers, what we often do is indeed some kind of like investigation, what their use cases and quantum algorithms, like how they line up, how excited should they be about developments in quantum computing. And so some of these projects have done looked at machine learning, but also a fair number of them have dealt with optimization questions. Optimization questions are, of course, ubiquitous in the world, I guess. Some things that we've done with BMW is fleet routing optimization. That's kind of very natural, and everybody worth their salt in algorithms knows that the traveling salesman problem is NP complete and therefore should be not solvable. Yet, in practice, people do it to a certain extent all the time because they have to. So they do it imperfectly, or they do it, on average case performance, but they care about these kinds of hard optimization problems tremendously. Robotic arm movement is another problem that has like an optimization flavor that we looked at together with the R&D departments at BMW. Airbus has been a is a company that has been interested in quantum computing for a really long time, and obviously they care about such a thing as fault-free diagnostics, where you kind of worry about like what would it mean for the system to completely fail, and so you really have to kind of like try out, as it were, all possible ways how things can fail and see, you know, which one leads to a fatal failure. So that is an optimization problem. And so when people design this, they kind of do this fault-free analysis all the time. And that's an expensive computation to do. And so the hope is that, you know, quantum algorithms, quantum heuristics are going to be helpful with that. So we looked at Airbus into that.
If it's not confidential, can you also like tell maybe which kind of hardware, maybe just in the like highest level, maybe gate-based or annealing-based optimization? What kind of optimization?
It tends to be both. It is so some of these customers, the projects were from a few years ago, but I think most of the times what you would see is that we have an optimization problems, and we try to solve it using a quantum annealer. Mm-hmm. So that would be the D-Wave quantum annealer in one of the installments that they've had over the years. And then we compare it with the circuit. So typically what we do is with a project like this is that we run it on the annealer, we run it on the circuit, and we try to kind of like learn like, okay, how do the two compare? And in neither case, we can solve like a commercially relevant problem for them yet, but you can then start to extrapolate like, okay, this is how the scaling works in the annealing context, this is how the scaling works in the circuit context. So we've tended to do both for these kinds of projects.
Sorry, one question about that, Wim. I'm kind of curious about how you do the comparison, if you can talk about that, because I mean, D-Wave's had thousands of qubits
right
for a while now, and still the largest circuit models are still in the hundreds. So I'm just curious about how that comparison is done.
To build on that question, I think at their last conference, D-Wave was claiming around 160 to 70 all connected graphs, solving those in their last annealer, the 5,000 qubit one. And when you look at another system like IonQ or like the gate-based ones, they're not on the hundreds range yet. They're mostly like 15 workable qubits. So how do you actually make the comparison, as Tom asked? Because the problem scales are kind of different, and they're different technologies as well. I'm assuming at gate-based you're doing something like QA, OA. So how do you like compare the solution quality as well?
Yes. So you really kind of, you do indeed. So take, you know, your standard optimization problem and let it be like a relatively nice one. That is a discrete one. And so, but maybe it's like integers, right? And so you kind of see like, okay, if I've got like so many integers, then I need so many qubits to kind of like encode these integers. And now there's going to be like some constraints on the integers, and you kind of have standard techniques for doing that. And so what you do is you kind of like take the problem of with an unspecified like size, and you kind of see like, okay, in the end of the day, how many qubits do I need on my annealer? And so there's all sorts of things, there are all sorts of reasons, and we don't have time to go into that now, but there are all sorts of reasons why, you know, the number of qubits of your problem is going to be much smaller than the number of qubits that the hardware uses to solve your problem. And so what you can do is you can like see how this scales. Like, okay, we could implement a, you know, 50 bit problem on this hardware. Now, extrapolating with this kind of like architectural layout, if I wanted to solve like 1,000 bit problem, how many qubits, how big should my annealer be? And so there you have some scaling, and this scaling tends to be, you know, at least quadratically, if not, you know, a higher degree polynomial. And then you can do the same thing for the circuits. You can like see like, okay, with a circuit, you have a different thing because the connectivity kind of works out differently because now you have more control over the gates. And maybe if constraints, there are like different ways of dealing with a constraint, different than the let's say the cubo approach of annealing. And so there then too, can you see like, well, in neither case, I can solve my desired 1000-bit problem, but qubit wise, how many qubits in a circuit do I need? And how many qubits in an annealer do I need? And then you can see like, well, what does that tell me for the long run? And so typically the setting is that the scaling for the circuit is much less dramatic than in the annealing one, because you've got more control of a circuit. And that then gives them, like us and our customers, a sense of where things are going. And in the long run, what is like a viable hardware approach for the problem sizes that they actually care about. I hope that kind of answered the question.
So can we?
Yes, thank you.
Can we run like QAOA on both an annealer and a gate-based, or would we have to?
No, you cannot run QAOA on an annealer, on a quantum annealer. No.
Yeah. Okay. So we're actually running different algorithms. Okay.
Yes. And the algorithms are kind of dictated, I would say, by the hardware. Now, of course, if you have a fully fledged quantum circuit, that's a universal computer. And so, in principle, any algorithm can be run on a circuit, but there's still going to be overhead because the connectivity of the circuit, matters a lot when you try to like embed some, arbitrary, say, a quantum Fourier transform, certain architectures. So it's we're really, in this day and age in quantum computing, kind of where I would say people were in like the 50s in classical computing, that you have to pay much more attention to the details of the hardware. We're kind of spoiled, right? We've got a laptop and, anything runs and we don't have to worry about these things. We just care about clock speed and that's about it. But yes, but there are many more details to kind of like be concerned about, also to predict the scaling. Because as we know, when we think of like superconducting quantum circuits, the connectivity going forward is going to be very different than the connectivity of say, an ion trap quantum computer. The latter having, a greater challenge to get more qubits, but having a much better connectivity. And to understand, how this trade-off is going to work out is something that is, important, and that needs to be kind of like figured out in the process.
Of course, yeah. So given an ideal gate-based quantum computer, universal, would that be preferable to a quantum annealer? Would it be more?
Oh, absolutely. Yes, okay. Because a quantum circuit can simulate an annealer, but doing it the other way around is much more difficult, if not impossible.
Okay, perfect.
Yeah.
Okay. So to the answer to the original question, and correct me if I'm wrong, Wim, but the comparison is actually like for gate-based and optimization on gate-based versus annealing is an asymptotic comparison. So in theory, you look at the scaling, and if there's actually not like an experimental comparison then.
Well, there is, because oh, sorry. So no, that's not what I meant. There is no like big O notation going on. It's more that we on the hardware that we have, we kind of like look at, well, if the problem size is size 5, if in the 10, 15, and we kind of see how that curve goes. Mm-hmm. Okay. And so we extrapolate from the experimental data that we have. That's the better way of explaining. Yeah, we extrapolate from the data that we're getting.
But you see confirmation on the theoretical fact that annealing scales more dramatically, whereas gate-based is more. It doesn't have.
Yes, that this is not always the case, but I would say for a typical optimization problem where connectivity between the different bits plays an important role, you do see that scaling effect, that the scaling of the annealer is more worrisome as the problem sizes that you want to solve get bigger and bigger. Okay. Yes, gas and oil is also an industry that has lots of optimization. Okay, I just want to get some important points across, honestly, in advertisement. And so one of them is that for some of you who are more new to the field, you might have like unrealistic expectations because of what people say or write in the well, I wouldn't say in the press, but what people say or write, and that hard optimization problems, NP hard optimization problems are most likely remain, hard even quantum mechanically. So we do not expect that quantum computers will be able to perfectly solve all our hard optimization problems. And so whenever somebody says something like quantum computers solve NP hard problems by trying out all options in parallel or in quantum parallel, that's somebody who's, doesn't know what they're talking about. So the quantum advantage that we're aiming for is much more subtle, I would say. We're aiming for polynomial speedups. We're aiming for heuristics that work better than classical heuristics. Maybe even a constant overhead is reduction is something worth pursuing. The speedups and the improvements that we're looking for is not, the gold standard is, of course, factorization. We think it's exponential. On a classical computer, it's a polynomial time. That's very specific for factorization. For a lot of other problems in optimization in machine learning, we're aiming for something more modest, but not necessarily, but probably more impactful because machine learning optimization, it's so important in general. And so here's something that some of you might be kind of thinking about, like, okay, well, what is the role? And this came up earlier in Matt's talk, like, what is the role of hardware versus software? Because it's not unreasonable to expect the kind of same exponential improvement rate in quantum hardware that we've seen in classical hardware, Moore's law. And so the hardware improvements classically have been, for a long time have been exponential. And, we probably will see something similar for quantum hardware. And then, of course, you think like, well, if the quantum hardware improves at an exponential rate, then right there, you have your exponential improvement. And so, why bother with software development? Like, isn't it all, like somebody just said earlier, aren't we just waiting for the hardware to get there? And that's all there is to it. So this is, why care about quantum algorithms? Why do we care about algorithms? A company like QC Ware, which is not a hardware company, like, why do we think that there's something to be had there? And as they say, if you want to get anything, if I want you to get anything out of this talk, it's this data. So this is, I'm going to spend definitely a few minutes talking about this. So this is about an article from 10 years ago, and this is about classical optimization, specifically linear programming. So linear programming is a way of solving optimization problems that have linear objective functions, linear cost functions, and linear constraints. And so the first thing to note is that this is an important general framework. Lots of problems can be phrased as a linear program. The confusing thing is that the problem is called linear programming. So but it's linear optimization. This is important, and already in the late 1940s, Danzig found like an algorithm to solve it, to solve linear programming. So I just kind of want you to stress that this algorithm was designed, written down on paper in the late 1940s. Then hardware comes around, and people start to see the commercial value of building these solvers and deploying them and making them available for users who are not like mathematicians. And so a very kind of like crucial attempt at this, or successful attempt, was Cplex. So it implements a way of solving these linear problems, and it does so using the language C, hence Cplex. And so this, you can still buy this. This has been around for several decades, and it started in the 1988. So that was Cplex 1.0, and it has gone through many iterations. It's now effectively owned by IBM, and so we have here like.
So just as a aside, if you're an academic email, you can sign up on IBM and download Cplex as a student for research purposes.
Yes, good to share that. Yes, indeed. And so what is really nice is that this is a very, on one hand, it has the full stack, as we like to say. You've got a mathematical problem, you've got a mathematical definition of the algorithm. Now you're going to have to implement it, and now you're going to have to like use it on cases that customers care about. And now you have like, because this has been going on for several decades, you see the role of like, well, the hardware improved over those decades, and the software improved, because Cplex 9.0 is different from Cplex 1.0. And so what was done in this article, or combinatorial optimization in action, is that they kind of took a case, a commercially relevant case of 1.5 million variables, and there are like 400,000 constraints and then some numbers, and they asked themselves like, well, this is a problem that we care about in the real world, and on the various moments in time, how long did it take Cplex to solve it? And what you kind of want to do is understand what the algorithmic component of the like, we've gotten better at this. Like, what is the algorithmic component of the speed up? So what they did is like, they took the algorithms in the various incarnations, and they ran it on the same machine, some like P4 machine, and they looked at like, well, how long did Cplex 1 take? Well, 30 days pretty much. And then 10 years later, they solved it in 1.5 hours, and then in 2003 they solved it in less than a minute. And so purely algorithmically, the algorithmic developments in the implementations of Cplex made that the overall speed up during this period of 15 years was like 43,500. That's the algorithmic speed up that he achieved. In the same period, the hardware had a speed up of 1,000. So this is like Moore's law, pretty much over a period of 15 years. So you see here that the algorithmic improvements are much more important than the hardware improvements. And this is not because like people came up with like fundamentally different algorithms. They just like, they fine-tuned it. They found like better kind of like heuristically developed techniques to do this. Like whenever you run an algorithm, there are many choices that you make, how you go about solving it, and you can get better and better at it. And so this, and then I'll get off my soapbox, but this, is a prime example of why algorithms matter. That, there are other examples out there. This is a fun topic to kind of like research, like with these problems that are important enough that people really try to get the algorithms better. It is absolutely the standard that the algorithmic improvements vastly outpace the hardware improvements. And so, yeah, this is why we care about quantum algorithms, because we fully expect that by getting better and better quantum algorithms, you're going to get like an improvement that is going to like more significant than the quantum hardware improvement in the long run. So that's why we care at QC Ware. That's why we care about quantum algorithms. And so it kind of goes to a kind of a motto that I try to instill at QC Ware is that if you want generic speed ups, you improve your hardware, right? You make it faster, give it more memory, stuff like that. But the dramatic speed up that you saw on the previous slide, that's because people really kind of like sat down and took that generic algorithm and fine-tuned it, improved it for the use cases that they care about. So if you want to have speedups for more specific problem instances, you want to improve your algorithms. And the bang for the buck that you can get is much larger by specializing your algorithms for the cases that you care about.
It's clear that like there is a very, very huge difference between like the algorithmic speed up. But do we see that, is there a smooth curve though, or is it more like specific breakthroughs that give us the algorithmic speed up? Because in hardware, you see a smooth curve. Every year there is an improvement. But isn't it that like in algorithmic development, you can see like years of no improvement and someone comes along and has a great idea and then you see like 100x speed up?
No, so it is yes. So you kind of like think of the plot, right? How it goes. And that's a good question. I should include a graph about this because people have really investigated this for algorithms in linear algebra. And so what you see is indeed a more kind of abrupt way, more kind of discontinuous way of how the algorithmic improvements come. But I would say that the algorithmic improvements still kind of happen, once every year or so, once every 2 years. That somebody has a good idea, like, oh, it goes up a little bit. So it's not as if it is like completely flat and then there's one brilliant idea and boom, where we have a 10,000, speed up. It does go, it is incremental stuff. There is, there's not like Cplex 1 and Cplex 2. There's like Cplex 1, 2, 3, 4, 5, 6, 7, 8, 9. Like these improvements happen, like yearly or every 2 years, that like a significant idea kind of like gives us another speed up of like a factor of 5, a factor of 10, something like that. And so it's not just like one brilliant person, this romantic idea, like one brilliant person that solves it all. Like these are team efforts. Somebody has a good idea, somebody else has another better idea, and so it goes. It is incremental in that sense.
Win, quick question, please. Sure. Okay. This might sound rather naive. I'm a self-learner, but very impressive about the traditional algorithm speedups and the heuristics behind them. Are they directly applicable to quantum? My sense is in quantum, the whole idea of an algorithm is different than what you were showing us about the
a quantum algorithm is the same way an algorithm as you have in a classical algorithm. It's more that this is a kind of well-studied use case where we have history, where we have the data. But when you look at, for example, the analysis that people have done on, okay, what is needed to break RSA, of a certain size, RSA encryption of a certain size. And you look in the literature, you will see that there's like the past like 10 years, there's been like a sequence of articles where people really reduced the quantum circuit size needed to break, RSA of a certain key size. So this is definitely, I would say, quite similar.
Thanks.
Okay. Yeah. Right. And so, oops, wrong direction. Right. And so optimization is there are many, like, it comes in many flavors. So you really need to kind of like understand what truly the optimization problem is that you try to solve. Like saying that you work in optimization is kind of like saying that you work in machine learning. Like it comes in so many different flavors. Like you need to be more specific than that. And what is really important, I would say, outside the academic world, is that you want to understand from your customers, what the problem characteristics are that you care about. Like how big is it? How do you do it nowadays? Are you okay with approximate answers? You need to understand everything as much as possible about, what people care about. And so I'll end with like an example of some recent work that we've done together with SRI International. This is a nonprofit research unit in the Bay Area and elsewhere, I should say. This was funded by the Air Force Research Lab, and this is about cybersecurity and the issue of how to deal with a distributed denial of service attack. The idea being that your gateways are being flooded with like bad traffic, and they kind of like clog up your system. So what you're going to do is you're going to turn off certain gateways to block as much bad traffic. But every time you turn off a gateway that has bad traffic, you're also blocking out some good traffic. So on the one hand, you want to block enough traffic so that you come under the capacity threshold of your incoming node. On the other hand, you want to maximize the amount of good traffic that kind of like survives your blocking. And so this is cybersecurity, but actually it's an optimization problem. And it's an optimization problem of the kind that we know as knapsack, where you try to optimize some like linear function where that is like the amount of good traffic that is being that you receive, while at the same time the blocking of the gateways is such that you kind of like resolve the flooding of the capacity of your incoming node. So why is it called knapsack? It's like you've got a backpack. It can hold up to 15 kilograms of items, and you want to maximize the value of the items in your knapsack while obeying the 15 kilogram limit. And so this is a studied problem. It's called knapsack, and it's NP hard to solve this in general perfectly. What we did was we looked at data of what happens with these kinds of denial of service attacks, and we kind of came up with scenarios of like specific DDoS knapsack instances. That's what we kind of like generate. That's like the data. And then we developed a quantum heuristic for it. And we compared it with like how this heuristic, this quantum heuristic like performed compared to classical heuristics. So we looked at how does simulated annealing, classical simulated annealing solve this? Or how does a classical greedy algorithm perform on these hard instances that we generated? And so I don't have the time to go into details, but what you see here on the right is all the dots are instances. And every time you see a blue dot, it's a case where our quantum heuristic performed better than some generalized simulated annealing approach. And whenever you see an orange dot, it meant that the classical heuristic worked better than our quantum heuristic. And so this is kind of what you should be expecting. This is like good news. You have a quantum heuristic which does not solve the problem perfectly. It's an NP-hard problem. You should expect it, but it's going to most of the times outperform your classical heuristics. And so we compared this quantum algorithm with a classical greedy algorithm, and 90% of the time our heuristic worked better than the classical greedy algorithm. And so this is this is what you should be thinking of where quantum optimization is going towards, tailor towards specific use cases, make it such that you do significantly better than your classical heuristics, and that's good. That's something that makes the world go around. And so I'll end with this: that the first useful quantum optimization algorithm for business applications, it will rely upon the whole stack. We need people who are experts in algorithms. We need people who are experts in coding. The quantum hardware folks have to be on board to kind of like get the best out of the hardware. And we need to understand what the problems are that the customers care about. A lot of research, for example, goes on in some problems like Maxcut. I've done it myself. That is not a commercially relevant case. So you really need to talk, all across from the top to the bottom of the stack to make this work. But it's very exciting, and the potential payoffs are tremendous, both financially and intellectually. And I'll leave it at that. Thank you.
Thank you, Wim. Thank you. Yeah. It's great that you ended on collaboration. That's what we're trying to achieve here. And as a person who has been in academia and industry, like in both ways, I think you have seen the importance of collaboration on both domains. And this space in particular quantum computing requires the expertise from like 5-6 different fields. So yeah, thank you for that. I think you have a hard stop at you had
it's a kind of boring meeting that I have to go to. So let's take 1 or 2 questions.
Okay.
I have one as a quick follow-up from my previous one. You mentioned in the previous slide about the impressive results with the quantum heuristic versus the classical heuristic. Is it possible, like, you know, in 30, 60 seconds to explain what makes the quantum heuristic quantum? Is it because it's using like Grover gates or you know, Grover algorithms or Shor algorithm?
Let me finish. It uses kind of the inspiration was a QA algorithm, but instead of it uses a pre-processed initial state. So standard QA optimization uses a uniform initial state. What we did is we had a classical preprocessor create a very specific quantum state and then let the quantum improve upon the preprocessed classical state. So yeah, that's actually, thanks for that. Actually, the algorithm that you came up with was a hybrid. Like it started off with a classical and then like a quantum dessert to like push the classical result further. Yeah.
Thanks. That's clarified.
Yeah, thank you, Nathan. That's one of the questions I had as well. Any other questions for me? Maybe one final question?
I guess like this might be a bit speculative, I don't know, but like, so when Google came out with a supremacy result or advantage result a few years ago, there was like an immediate response from the sort of classical computing communities to try and show that you could do what they did with a classical computer. And I'm not going to like comment on that because, you know, I don't understand it well enough. But by sort of working on these algorithms in a more closed sort of proprietary context, do you think there's perhaps a worry that you come up with your algorithm and you think it's like going to beat any of the best classical algorithms, and then because you're not exposing it to the sort of global community of classical optimization experts, your algorithm might not perform as well as it might not perform that much better than the sort of best classical algorithms could do? That makes any sense?
Yeah, so there is definitely a kind of spectrum of scenarios here. Now, one of them is indeed, so when you look at something like, say, Cplex, this is like a relatively general purpose package of software. And then you've got like knobs that you can tweak to kind of like make it work for your specific instance. Now, that is software that is, you know, available, and people can, you know, people do this, right? They run competitions. Every year there's like a satisfiability competition. And there, you know, the problem with these competitions is that typically you have to disclose, you know, your full software, and you might not want to do that if you have a commercial project. But as soon as, you know, you try to start, you know, selling your solution one way or the other, people can start to compare it. And so in that sense, you know, the hope would be that in a way, the financial incentives make that, you know, well, if there is a better classical solution, then those people should like build that and start selling that to the people who use my quantum solution. So that's kind of how we hope, you know, it kind of that's how it should work.
Yeah, cool. Yeah, makes sense.
I have one question, and this relates to the sort of annealing and gate-based computation method. So when you were just talking about quantum heuristics, right? I'm assuming that was, and QA, which is in reference to a gate-based quantum computer. How different are your heuristic approaches towards designing algorithms on like annealers? Like, are they very different? Do you go in with the same idea of, you know, you have some set solution, you try to improve upon that, or is there like is there any, like, I'm assuming there is a difference, but like, is it a significant difference or?
Yeah, so because I mean, annealing can go by many names, and there is, you know, a way of talking about quantum annealing that can implement universal quantum computing, but that's not currently what the hardware of D-Wave does. But kind of by and large, what you see is that when you have a circuit, there are like many different things that you can do with the circuit, like individual gates. So you really have there like a Swiss Army knife of like possibilities of how you can try to attack your problem. If you have an annealer, you kind of have a hammer. Like it can do one thing, it's really good at it, but you've got far fewer, you know, tricks up your sleeve that you can apply. And so in that sense, the amount of ingenuity that you can like throw at the problem is much larger in the circuit because there's just many more things that you can do with the circuit.
Okay. Yeah. Okay. I see. That makes sense. So your approaches have to be fundamentally a bit different because of your limited options when it comes to flexibility in the annealer.
Yes. Right. Yes. The algorithms will be. Sometimes there is some kind of correspondence. Some people would say that there is a correspondence between QAOA and quantum annealing. I think Eddie Farry disagrees with that. But when you go to, you know, algorithms that go far beyond, you know, quantum annealing, where, you know, you've got pre-processing, post-processing, feedback loops, all these tricks that you can do, the comparison kind of starts to, from an algorithmic point of view, the comparison starts to break down because you cannot do these things really on an annealer.
Sure, thanks.
Okay, thank you, Wim. We reached the end of our session, and in this session we hosted QC Ware. I'm gonna stick around for a few more minutes. On our next session, which is gonna be on again the last Wednesday of the month, we're gonna be having speakers from QuConv, so feel free to join it. Again, thanks for all of your time. I'm gonna be sticking around, but I'm gonna stop the recording now. So if you want to chat.
Okay, right.